Section 12.6 is linear correlation and regression. In this section, we're going to talk about what linear correlation is, how to calculate the correlation coefficient R, just a general coverage of what linear regression is, and how to calculate the line of best fit. That line of best fit will be used to make predictions. We're going to do all of these calculations in our calculator because they can be very, very time consuming and tedious by hand. First, a few definitions. Correlation is just used to determine whether there's a linear relationship between two quantities, and if so, how strong the relationship is. Regression is going to be used to determine the equation that relates the two quantities. The linear correlation coefficient R is a unitless measure, which just means it doesn't have a label on it like feet or inches, and it describes the strength of the linear relationship between the two variables. If the value is positive, then that means as one of the variables goes up, the other variable also goes up. If the value is negative, then as one variable increases, the other decreases. The letter R, the correlation coefficient, is always going to be between -1 and +1. And they say inclusive because it is allowed to equal -1 and +1. Scatter diagrams or scatter plots is a visual aid that can help you see if there's a correlation or not when you plot the bivariate points. Bivariate just means there's more than one, there's an x and a y, which we of course need to plot. The independent variable is your x variable, and it is typically your quantity that can be controlled. It's going to go on your horizontal axis. The dependent variable is your y variable. It is going to respond to the x, and it is going to go on the vertical axis. The value of R is a measure of how far a set of points varies from a straight line. So the more the points are spread out, the less they look like a line, the weaker the correlation is, and the closer the R value will be to 0. The smaller the spread, the more like a line the points look, the closer the R values will be to 1 or -1. And it just depends on whether the graph goes uphill, if it's +1, or downhill, it'll be -1. So I have some examples here for you of some positive correlations. Notice in general, these should kind of all look like they're increasing over time. The first example, all of the dots are in a line. That is the strongest positive correlation you can get, and notice that that is going to have an R value of 1. Now notice in the second example, the dots are moving in an upward pattern, but they're a little more spread out. They are not all in a line. So this R value is going to be greater than 0 because it's positive, but it's not going to be as large as 1. It could be something like 0.5. And then again, we'll go to a third example where we're still clearly going uphill, but there's a lot more spread between our points away from the line. So this is a weaker relation, and it's going to be even closer to 0. And then the last example, I don't see a linear relationship at all. I can't really tell, is it going uphill? Is it going downhill? It just looks like a glob of points. That would have no correlation at all, and it would have an R value that's pretty much 0. These are all some examples of some negative correlations. Notice your first is all points in a line going downhill. Notice the R value is a -1. That's as strong as you can get. And then as they spread away from the line, the R value is going to get closer to 0. And if you can't see a pattern at all, and you don't know if it's going up or going down, your R value would be 0. Now, look at this crazy formula to calculate the correlation coefficient R. It is very, very tedious to do by hand. So we are actually not going to calculate it by hand. We're going to do all of these calculations in our TI-84. Let's look at an example. Egan Electronics provided the following daily records about the number of assembly line workers absent and the number of defective parts produced for 6 days. Determine the correlation coefficient between the number of workers absent and the number of defective parts produced. I have the data on the next slide. So there's 6 days. The numbers 1 through 6 do not need to be included when you go to calculate, but it's just helped to keep you organized. So when there was 3 workers absent, 15 defective parts. When there was 5 workers absent, there was 22 defective parts. When no one was absent, 7 defective parts. 1 person was absent, 12 defective parts. When 2 people were absent, 20 defective parts. And when 6 people were absent, there was 30 defective parts. Okay, so we want to see if there is a correlation here. And again, we said it was too tedious to do this by hand, so we're going to do it with our calculator. So let me create a video that shows you how to enter this in your calculator to find your R value. Okay. I'm going to scoot this data up so that we can use it when we're looking in our calculator. Okay, so the first thing we need to do is we need to get the data entered. So to do this, I am going to press second catalog. The catalog is down here, your 0 key. It's going to pull up this big long menu. You need to scroll down until you see what says Diagnostic On. You only need to do this step once. Once it's on, it should stay on, but you have to get it turned on at the beginning or it's not going to work. Come on. Getting closer. Aha. Okay, so see there's a diagnostic off and a diagnostic on. We want the diagnostic to be on. So when your arrow's pointed to that, go ahead and hit enter 2 times. And that'll turn the diagnostic on. And again, you should be good to go now. Now we need to put our data in. So you need to hit the button that says Stat. And we're going to edit, so you should already be on edit. If you have anything typed in list 1 or list 2, you need to take it out. So to do that, you just go up to the L1 and you need to hit the button that says clear and then enter. Now we're going to put all of our data points in. So we're going to put the worker's absent number in the first column. So we have a 3, 5, 0, 1, 2, 6. And then we'll put the defective parts in the second column. 15, 22, 7, 12, 20, 30. Okay, once you have your data in there, you can go ahead and hit second quit to get out of there. You'll go back to your home screen, and now you are going to put the stat button again. But this time you need to go over to the menu that says Calc. And we want option number 4, which is Lin Reg. And we're going to hit list 1 is already should be in there. Your default is that you want your X to be list 1 and your Y to be list 2. You do not need to enter anything for your frequency list. We do not need to store the equation, and we can go ahead and hit calculate. Okay, now they're writing an equation of a line. The A value represents the slope of your line. The B value is the y-intercept of your line. What you're looking for is that R value. Our R value is 0.9219. Okay, so our correlation coefficient R is 0.9219. So what that means is there is a strong positive correlation between the number of workers that are absent and the number of defective parts. If you want to plot it just to make sure, because you want to make sure it makes sense to you, you can definitely plot it. So we can put the number of absent workers on the x-axis, and we need to get from 0 to 6. we're going to put the number of defective parts on the y-axis, and we need to get up to 30. So I'm going to count by fives. 5, 10, 15, 20, 25, 30. And then we can plot our points. 3 produced 15 errors. 5 produced 22 errors. 0, there was still 7 errors. 1, there was 12 errors. 2, there was 20 errors. And 6, there was 30 errors. So, if you look in general, it appears that the data does seem to be following a positive pattern, okay? And then if you wanted, they told us earlier that the A value was 3.2 and the B value was 8. That's actually writing the equation for you of that line I just drew. So it's just like saying y equals 3.2x plus 8. So you would have your y-intercept be at 8, and then your slope would be positive 3. So what I just did when I drew that line and wrote the equation of that line, that's called a linear regression. The linear regression is forming the relationship between the two variables so that you can use it to make predictions later on. The linear regression line is called the line of best fit. It's also called the regression line or the least squares line. And it's also another horrendous formula. This is the crazy formula to create the line of best fit. Notice they're writing it in the form of y equals mx plus b. You can do all this fun stuff if you want to, or like I just showed you on the last example, you can do it in your calculator. So, in the previous example 1, we used the line of best fit feature to create our equation. So just to remind you, I'll show you what that looks like again. So if you notice here, when we ran the lin-reg, we had an A value of 3.23. We had a B value of 8.52. That is what's going to be used to write our equation in the form of y equals mx plus b. So the line of best fit would be 3.23x plus 8.52. Now, I do want to bring up one more topic, and it is the topic of alpha and critical values. A lot of times they're going to ask you if your R value is an appropriate number based on the alpha value. So let's use the example that we did previously. In that example, we talked about 6 days, so our N value would be 6. We calculated an R value of 0.92. And let's just say they asked you to have a level of significance of 0.05. Okay, what you have to do in this situation is you have to look at the critical values table to make sure that your R value is appropriate. If your R value is not appropriate, then that means you don't have enough data to complete your problem. Okay, so here's the rules. What you need to do is you need to take the absolute value of your R value, which ours is 0.92. And then you need to go to the table, you need to look up the alpha value for the proper N, and you need to see if your R value is bigger than the number in the table. If the R value is larger than the number of the table, then there is a correlation. So if R is larger than the table, there is a correlation. If the R value is smaller than the number in the table, there is no correlation. Don't try to write a line of best fit. So let me just show you that table so that you can see it. It is in your book on page 787. I also put it in the online notes for you in chapter 12 notes. Okay, so you have this table in your book on page 787. And notice the N is on the left and the alpha is on the top. You have two different alpha values. These are called levels of significance. You have alpha equals 0.05 or alpha equals 0.01. So our n was a 6. So we're going to look at the 6. And our level of significance I told you to look at was 0.05. So what you want to do is you want to look at that number, which was 0.811. If our R value is bigger than this, there is a linear correlation. Our R value was 0.92, so we are good to go. We would have to be very careful if we went to the alpha equals 0.01 because we're getting really close and it would not be linear compared to this value right here. So there are some homework questions about that. Just make sure you use the table and you're always wanting your R value to be larger than the number in the table.